Hey guys, in this video we're going to continue our talk about gases, and we're going to talk about what's called the named gas laws. We have several named gas laws. We have Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, the combined gas law, and the ideal gas law. So when we think about a gas, we usually think about a couple of gas variables. Of course, one we've already explored is pressure. So gas pressure, how much force is being applied by that gas. But some other important things that we're going to look at is volume. So how much space does that gas occupy? I'm not talking about the particles themselves, I'm talking about the gas itself. How much space does that gas occupy? We're going to look at temperature. A gas is very tied to, its properties is very tied to the amount of kinetic energy it has, so temperature is very important here. And then, of course, how much we have, so our number of moles of gas. So these are the four gas variables we're going to be looking at when we're thinking about our gas laws. So let's start by thinking about a system where we have the number of moles in our gas and our temperature staying constant. So our first system, moles of gas and temperature remain constant. So generally when we're thinking about here, we're thinking about a gas in a balloon or some other flexible container. So here we have a set amount of gas molecules, but we have a flexible container, so the volume can increase or decrease. So our volume can change, and pressure. Also with a flexible container, like a balloon, the pressure on the inside of the gas is the same as the atmospheric pressure. So the pressure of our gas, the pressure of our atmosphere will be equal for a flexible container. If the pressure inside the gas was greater, it would push and expand out. If the gas or the pressure outside the atmospheric pressure was greater, then it would compress the balloon. So we've got an equal pressure on both sides. Okay. So what we're looking at here are our two other variables, pressure and volume. So let's think about what happens. So if we have a gas where we increase the pressure on that gas, it's going to cause that volume to decrease. So an increase in pressure will result in a decrease in volume. Okay, so as we take our balloon and we apply pressure to that balloon, so our atmospheric pressure becomes greater, the volume of that balloon becomes less. And then vice versa, decrease in pressure results in a increase in volume. So if you take and you lessen the atmospheric pressure, your balloon is going to become larger. So we see that the pressure times by the volume is equal to a constant Kb. This Kb is Boyle's constant, named after Boyle, who came up with this law. So if the constant, if we keep the same gas, we don't change anything about it, we don't change the temperature, and we don't change the number of moles, then our Kb will stay the same. It's a constant. So we'd say that P1, V1 would be equal to P2, V2. So if we change the pressure, we can calculate the volume of that gas. So as we increase the pressure, we will decrease the volume and so on and so forth. Next thing we want to look at is temperature and volume. So here we are going to deal with a rigid or a flexible container again. So it's our next system. We still have a flexible container, but now we're going to keep pressure constant and our number of moles constant. So in this case, we are looking at our volume and our temperature. So what happens to one as we change the other? If we have a gas within a balloon and we heat up that gas, that's going to increase the kinetic energy of that gas, and it's going to expand, especially if we're in a container where we can flex. So we have that ability to flex where our atmospheric pressure is going to be equal to our gas pressure. So here, we're going to increase temperature. Our particles are going to move more and more and more. That's going to cause them to expand. And as we increase temperature, we're going to increase our volume. So increase in temp, expansion of the gas, and that's going to cause a increase in volume. So we'd say that temperature and volume are directly proportional. So as you increase as you increase temperature, you increase volume. So we'd say V over T will be equal to a constant, our Charles constant. Oh, by the way, this is Boyle's law. And again, as long as we keep the same number of moles of gas and we keep our pressure constant, then this will stay constant and we could set up our Charles law. Okay. Next system we want to think about. Now we're going to think about a inflexible or rigid container. Because we have a rigid container, and because we still have a container, we have set number of moles. So our constants here are moles of gas, and we're rigid, so our volume is also going to be constant. So here we are looking at pressure and temperature. So let's think about what happens as we increase the temperature of a gas. Generally, if you increase the temperature of the gas, you're going to expand. But we do not have the ability to expand because we're in a rigid container. Therefore, all we're going to do is increase the number of collisions the gas particles have with the walls of their container. So we increase temp. This is going to increase collisions of gas particles with the walls of their container. That is means an increase in force. So more gas collisions leads to greater gas pressure. So as we increase our temperature in a rigid container, we are going to increase our pressure. So our pressure over our temperature is going to equal a constant, which we're going to call the Gay-Lustig constant. And if we stay in that rigid container and we don't add any more gas molecules, then we could say that our pressure and our temperature can be observed. See what happens as we change one of them. This is our Gay-Lussig's law. Okay, so we're going to pause for just 1 second from talking about gas laws to talking about something important in gas laws, which is standard temperature and pressure. When we have a gas, we generally get data such as density under common conditions, which are our standard temperature and pressure. So these are our common conditions. And our standard temperature is going to be 273.15 Kelvin. By the way, as a note, we always use Kelvin when we're talking about a gas. We do not talk about any other unit. And that's because our temperature determines our kinetic energy, right? Or our molecular motion. If we have 0 Kelvin, that is the only point when we have no molecular motion. At any other point, we have molecular motion. So when we're thinking about like 0 degrees Celsius, that does not mean we don't have molecular motion, but that's what we would get if we put that into equation. So always, always, always use Kelvin when doing calculations for gases. And then our standard pressure, this is going to be 1 atmosphere or 760 millimeters of mercury or 760 torr. Okay, so let's try an example. We have 2.50 liters of a gas at some pressure. At standard pressure, it has a volume of 8.00 liters. We want to know what this pressure is. We can see here, we've got just pressure and volume. We assume that the rest of it is staying constant. So if we're just talking about pressure and volume, we are talking about Boyle's law. So this is our V1, our P1, our V2, our P2. We just plug and chug. So P1 is equal to P1 times by 2.50 liters is equal to our P2, 1.00 atmospheres, times by our V2, 8.00 liters. Calculate this out, we get a P2 equal 3.20 atmospheres. In this case, it doesn't matter what volume or pressure you use because you'll just get the volume and pressure of the other variable. the other set of conditions. As long as you stay the same for your volume, stay the same for your pressure, it doesn't matter what you use. Okay, next question. So, in the next example, we have a sample of hydrogen with an initial temperature of 50.0 degrees Celsius, and it is lowered, giving a temperature of negative 5.0 degrees Celsius. At that lowered temperature, we have a volume of 212 centimeters cubed, and we want to know what our initial volume is in decimeters cubed. So, first thing we should do, anytime we see a temperature in a gas problem, we need to convert that into Kelvin. So we have 50 degrees Celsius, we add 273.2, that gives us 323.2 Kelvin. If we have our negative 5 degrees Celsius, add 273.2 to that, we get 268.2 Kelvin. Okay. And then we want to go ahead and also convert our volume into decimeters cubed. So to go from centimeters cubed to decimeters cubed, there is 10 centimeters per 1 decimeter. And we will cube that, giving us a value of 0.212 decimeters cubed. Now we're going to put this into our equation. V1 over T1 is equal to V2 over T2. Only things that are changing are temperature and volume. So we're talking about Charles' law here. So we have V1 divided by T1, 323.2 Kelvin, is equal to our V2, 0.212 decimeters cubed, divided by our T2, 268.2 Kelvin. At this point, you should kind of think about what should occur, right? We should expect, since we are lowering our temperature, we should expect our volume to lower. So when we do this, so this one, this lower temperature, should have a smaller volume. Here, we have a higher temperature, so we should have a higher volume. So when we solve for our V1, doing just simple math, we get 0.255 decimeters cubed. And hopefully that is what you would expect to happen. You would expect it to go up in volume because it is a higher temperature for our unknown. Okay, let's try one more example before we go on to other gas laws. Here we have a sample of O2 in a cylinder under 2 atmospheres of pressure. So the pressure here is equal to 2.00 atmospheres. And it's occupying 500 milliliters and its temperature is at 25.0 degrees Celsius. It is in a cylinder, and anytime we see cylinder, we assume rigid container. So volume does not change. We're going to go and we're going to see at what pressure the sample will have when we're at 0 degrees Celsius. So if we are at 0.0 degrees Celsius, what is our pressure? And this is the same here because we're in a rigid container. Again, the first thing you should do is convert into Kelvin. So add our 273.2 to 25, giving us 298.2. And then our T2, 0 plus 273.2 would give us 273.2. And now we can go into our Gay-Lussac's law. P1, T1 is equal to P2 T2. So our initial pressure, 2.00 atmospheres. Our initial temperature, 298.2 Kelvin. We are looking at a lower temperature, so we should expect a lower pressure. So 273.2 Kelvin will give us a pressure that should be lower. And when we solve for this, we get a P2 equal to 1.83 atmospheres, which is in fact lower in pressure. Okay, we can take all the laws we've just looked at and get what's called the combined gas law. Where our combined gas law combines all of our gas laws. So we first have our Boyle's law added in here. And then we want to combine our Charles law in here. So we divide by temperature. And that also includes our Gay-Lussac's law. So we've got P1 V1 equals P2 V2. So our Boyle's law. We have V1 T1 equals V2 T2, our Charles law. And then we have P1 T1 over P2. P1 over T1 equals P2 over T2, giving us our Gay-Lussac's law. So we have all three laws within this combined gas law. So let's see how we would use this. We have a 20-liter container and is filled with helium at a pressure of 150 atmospheres and a temperature of 30 degrees Celsius. Wants to know how many 5-liter balloons can be filled when the temperature is 22 degrees Celsius and the atmospheric pressure is 755 millimeters of mercury. So we want to know basically what the volume of this is when we reduce our pressure to 755 millimeters of mercury and our temperature to 22 degrees Celsius. So basically we're asking if we've got a cylinder, and this is a cylinder again, that contains 20 liters of a gas at 150 atmospheres of pressure and 30 degrees Celsius. If we use that to fill up balloons, so this would be a balloon cylinder or a helium cylinder, we use it to fill up balloons, how much will that gas expand to once we take it out of that cylinder and allow it to expand, bringing it to roughly atmospheric pressure and roughly room temperature? First thing we want to do, unit conversions. We're going to convert all of our temperatures into Kelvin. So we're going to add 273 to our 30. I'm only adding 273 instead of 273.2 because there is no decimal. So think about our sig figs. So this will be 303 Kelvin. And then our T2 will go to 295 Kelvin. We have our pressures in atmospheres and millimeters of mercury. I don't really care which way you change it. I'm going to change it from millimeters of mercury into atmosphere. So we'll take and divide this by 760 millimeters of mercury, giving us 0.993 atmospheres. Now all the units are the same, and we also have Kelvin. So now it's just going to go into our combined gas law, where our P1 is 150 atmospheres. Our V1 is 20 liters. Our T1 is 303 Kelvin. This will be equal to our V2, which is what we're solving for. Our P2, 0.993 atmospheres, divided by our T2, 295 Kelvin. And when we solve for this, we get a V2 equal to 2,940 liters. And from this, we now still want to know how many 5-liter balloons we can fill up using this. So we're going to take and say, okay, for every one balloon, we have 5 liters. And this gives us 588 balloons. Fantastic. Okay, next is our Avogadro's law. So the next system we're going to look at, we have pressure and temperature fixed. So here we are changing amount and volume. Okay, so we're basically filling a balloon. Or other flexible container. So hopefully, as soon as you think about filling up a balloon, as many people have done, you think about the volume increasing. So as you increase your number of moles, where n, little n, is moles, and then as you increase the number of moles, that will increase your volume. So our n, our number of moles, it is no longer our energy level in this chapter, n is our number of moles, will be directly proportional to our volume. So we'd say V over N is equal to a constant, which we're going to call Avogadro's constant. And keeping our pressure and our temperature the same, we can set up Avogadro's law. Which is very simple to use, but I'll go over it just in case. So let's say we have 1.00 grams of carbon dioxide, which has a volume of, in a balloon, that has a volume of 0.556 liters. If we add 1.00 grams of carbon dioxide, what is our volume? So the first thing we need to do is we need to convert these into moles. So 1.00 grams of carbon dioxide use our molar mass. We get to 0.0227 moles of carbon dioxide. And then this is 2.00 grams of carbon dioxide. So we'll do the same thing. Giving us 0.0454 moles of carbon dioxide. We can then put this into our V1, N1 equals V2, N2. So our initial volume is 0.556 liters. Initial number of moles, 0.0227. Our N volume is what we're solving for. Our N number of moles, 0.0454 moles. And when we solve for this, we get a V2 equal to 1.11 liters. So you should be able to write out a summary of the named laws. So if we think about all of our laws, you need to be able to come up with their names, what law they represent, and the constants. So let's see. This would be an example of something you would need to fill out on a test where you've got your different names of your laws, which you should know. You should be able to fill out the laws themselves, and you should know what the constants of those laws are. Okay, next thing we're going to talk about is the ideal gas law, which incorporates all the components of the gas laws we've looked at so far. It is lovingly referred to as PivNert. PV equals NRT, PivNert, where P is your pressure, generally in atmospheres. V is your volume, generally in liters. N is your moles, in moles. R is your gas constant or proportionality constant. And your T is your temperature, always in Kelvin. So our gas constant, the other units we use, pressure and volume, namely, will be based upon what gas constant we use. So our R, our gas constant, as I said, is a proportionality constant. Meaning that it's going to relate all of the different variables within the gas. We have all these units, we have to have something that's going to relate them all. So our gas constant has a couple different values depending on what units we use. So let's go through our two most common, 0.08206. This is the one you will almost always use for this chapter. So in this case, we need to have our pressure in atmosphere. We need to have our volume in liters. And then, of course, moles in Kelvin. So those are givens. We will look at this next one in 1212. But it's still a gas constant, but this is when we're looking at energy. So the first gas constant is when we're looking at pressure. The next one, we're looking at energy. Another one that gets used in this chapter is 62.36 liters times by torr divided by mole times by Kelvin. So in this case, we have a different pressure. And there are two other ones. Another energy one that we would see is 1.987 calories per mole times by Kelvin. And then another pressure one we might see is 8.314 meters cubed times by pascals divided by moles times by Kelvin. So this one is the one we will be using almost entirely for this chapter. You may see this one if I give you torr, you can use that. I'll put both those on a test. Okay, let's try a couple of quick examples with our ideal gas law, because this is the thing we're going to use the most. So let's say we take a canister, an aerosol canister, and we throw it in a campfire. So if we have a 1.0 liter canister and it holds 2.0 moles of gas, and the campfire temperature is 1400 degrees Celsius, we want to know what the pressure is. So we throw it in a PivNert. The only thing we need to change in this case is our temperature. Add 273. We get 1673 for our temperature. And then the rest of it can just go into PivNert. So P times by 1.0 liters is equal to 2.0 moles times by our gas constant, 0.08206 liters atmospheres, moles Kelvin, times by 1673. and we get a pressure equal to 275 atmospheres, which is very large and more than likely a pressure that is not going to be sustainable, so it would probably explode. Okay, next, we want to know number of moles of N2 that are in a 30.0 liter scuba canister if our temperature is at 300 Kelvin and our pressure is at 200 atmosphere. So again, we'll go through, put this in a pivnerd. We have 200 atmospheres times by our 30 liters equal to our number of moles, which is what we're solving for, our gas constant, and then times by our temperature. Solve for this, we get a mole amount equal to 244 moles. Then I could ask, okay, if we bring this to atmospheric pressure, how much volume would that occupy? So if we're at 1 atmosphere, and from here, we would get a volume equal to 6,007 liters. So if we allow that 30-liter container to expand out, it would be 6,007 liters. Okay, that is everything. Bye, guys.